Hello everyone, this is lecture 21 of Petroleum Reservoir Geomechanics, PTRE 465531. Last time we introduced module 3, which talks now about failure mechanisms, plural, when it comes to rocks. First module, we talked about external stresses applied, external conditions applied. Second module, we talked about interactions within the rock between the stress and deformation. We learned how to model it mathematically, how to characterize it. And now we will learn how does the rock break, okay? There is some mathematical criteria that need to be satisfied in order to have failure. Like for the mode 1 failures that we already talked in class in the first module, it's about tensile failure. So basically, you have to have the most tensile of all stresses, that is the least compressive in that case, to exceed the tensile strength of the rock that you're trying to break. And I'm using negative for the T because for the conversion that we are using in petroleum engineering, compressive stresses are negative. So this is what I'm trying to satisfy. Okay, this is what I'm trying to satisfy. Always when you hear about the tensile failure criterion, this is the equation. And then there is a little bit of thinking, what is S sigma 3? It may not always be one of the in situ stresses. If you remember last lecture, what Hakim was alluding to was basically, okay, when you get close to the wellbore, you have interference from the wellbore. So maybe those three stresses that we talk about, SH max, SH mean, and SV, are no longer the dominant stresses in that region. Maybe you have different kind of stresses. And that's true, but it's coming later. We're going to talk about the near wellbore stresses, which is a different set of stresses in cylindrical coordinates. That is the tensile failure criterion for mode 1 fractions. And then you have mode 2 and mode 3, which are both shear in plane, the sliding mode, and the tearing mode, mode 3, out of plane, which is basically excuse me, T, hot T. Basically the mode 3, tearing mode. And those are both shear. Unfortunately, for shear failure, it's not that easy. It's not that simple as the tensile failure. You have to measure we talk about shear stresses, tau, and or sometimes tau ij before. Sometimes we call the sigma ij. Just remember, if the I and the J are not the same, it's no longer normal, it's basically shear stress. So automatically it implies a shear stress. But we have to relate those shear stresses to the normal stresses, sorry. To the normal stresses. I use sigma n for the normal stress that we are looking for specifically. Some people use sigma n, some people may use a different nomenclature. I know that's because geomechanics is a little bit of and solid mechanics in general. It's like it has overlap with many other applications disciplines. Like petroleum, we are looking for geomechanics, right? Civil engineering, geotechnical stuff. Again, you are looking at the subsurface. But aerospace engineering, you have material science and engineering, you have industrial engineering. They all have a stake into solid mechanics, and that's like becomes a little bit of a. I read papers in geomechanics, and many times I don't know the symbols. So, yeah. Anyway, but we did talk about generally that the shear, the tau, is basically evaluated from different stresses, two other stresses. And it's compared with the normal stress, and whether some criteria that we're going to see later is satisfied, it will indicate us whether we have failure or not failure. Three types of failure. We have the tension, that's the mode one. We have the shear compressive, and we have shear collapse as well, which is basically, I have an animation for that. I think I made it work last time. Let me see if I make it work now. No, come on. I want it to be, hey, Malek. Last time I made it work, it was going slowly. There you go. That's the collapse, which we are really not gonna talk much about in this class, but we talk about, are you okay?
Yeah.
We talk about collapse a lot in drilling 411, about casing collapse and stuff. It's not gonna be a big theme in this class. If we have a lot of time at the end of the semester, maybe I can show some slides on collapse, but it's not really common reservoir geomechanics wise for the stuff that we are looking about. And actually, if you read the drilling books, when they are talking about casing collapse, they really use mechanical engineering notation. They have compression negative, tension positive, so it's a little bit confusing for the students there. Yeah, and then we talked about tensile failure, okay, in more detail, and we arrived to the Brazilian test, which is a very smartly designed way where you can use a loading frame, which is basically those loading frames are very simple devices. They are complicated, expensive devices, but they have a simple task. You have a plate that you see here, and you have the little cylinder on top, which applies the stress, the plate, and this thing here, which is fixed. And then you start making it move upwards. The plate moves upwards very, very slowly. 0.002 inches. I mean, it's something crazy, something very, very small. And it moves up. And we said that it creates, okay, compression here, point load. Oops. Sorry. So point load, and then by Newton's third, point load on top. And therefore, you have tension on the sides. And the material will fail. Sorry, guys. I pressed. No, it's my mistake. I didn't press this. The material fails generally. It's 10 times easier to fail in tension than roughly than compression, and therefore any tensile failure would happen in advance. And basically, we get the failure there. We measure the pound force at which I have the failure. This is F max in pound force. I divide by pi the length of the cylinder and the R, the radius of the cylinder, and I get my value of T. But remember, when I I will get the value of t, it will be a positive value, like we saw in the example problem number 1. But when I put it in my equations, I have to put it as negative because all my equations have tension as negative. And we call this the Brazilian test. It's a very, very easy, smartly designed test by Fernando Carneiro. And we had a whole discussion about it last time. And then we saw a example problem that was fairly simple to do. Just plug in the numbers, you are given the equation, very, very simple stuff. And these values are typical for gypsum plaster. I don't remember where I got this data, but it must be one of my old ones. I used to do a lot of Brazilian tests on different samples. Like this one was bulletproof glass, PMMA. It's 10,000 PSI, the tension of that. That means that if you want to use a material that will inject fluid and have it break, like rock breaks, it has to be able to sustain everything in the system. This to be able to sustain 10,000 PSI. For us in Texas, it was a little bit too much because we had valves and everything that were rated much lower. But I know in Colorado School of Mines, they have done it. And there are several YouTube videos where they do hydraulic fracturing using epoxy as a fracturing fluid of PMMA blocks from 10, 11 years ago. And when I was in Colorado School of Mines, I was working for that particular professor. He moved from petroleum to civil engineering and was doing tunnels, but I have seen his samples that are broken. He has the shelves in his lab full of samples that were used in the past. Yeah, bulletproof glass is very, very. And I would also say, if you are using the version that has two resins that are mixed together, make sure you do that in the fume cupboard and don't have your face near them. I know there is some weird chemicals involved. For some reason, whenever I was breathing this stuff, even a little bit, like I was having trouble in breathing the whole night. Mm-hmm. Because I remember I was doing experiments, I was doing the samples on Tuesdays, and then I was testing them on Friday or something. And I think I was going to Buffalo Wild Wings on Tuesdays because it was buy one, get one. And I was sitting at the bar and I barely couldn't breathe. I was like, I need to put force to breathe. For some reason, I must be allergic or something to some of those smells. Then I was like, it's better with gelatin, you know? Yeah. That's why I don't have Kalu use this stuff in the lab, you know? Oh yeah, Kalu. We spent last night grading the drilling exams, and you should expect the grades for these exams, the Geomechanics exams, end of the week, Monday night, Monday night the latest, something like that. Actually, it should be quick because it's less students in this class than in drilling. But yeah, something like that. And we have a little bit of time until homework 3. I told the drilling class, if you got a grade that you don't like, something must change. And it's not necessarily a hard change. It's not necessarily a difficult change. It might be, maybe you give too much attention to details that you shouldn't give and less attention to other more serious stuff on your revision. Maybe the nature of the problems you are not used to, you will be getting used to, but it's not the end of the world if you got a bad grade in the first exam, because as long as it wasn't a terrible grade, which means you really didn't do anything. Like unless you went there and you wrote your name and some other stuff and you got like 18 or something. Okay, that would be hard to come back from. But if it's a grade that is not necessarily bad, but a grade that you didn't like, I think you have plenty of chances to come back. We have at least 2 more homeworks and 2 more exams, so a lot of chances. Okay, we have T. How do we input it into our equations now that we have T? Remember, this is the tensile failure criterion. And we know that mode 1 fractures propagate in a plane orthogonal to sigma 3. So this least compressive stress is not always an in situ principal stress, but it will always have to be a normal stress because of the nature of the fracture, the way it opens. It won't be a shear stress, okay? And this alludes towards basically what we are gonna see later, the stuff that Hakim was alluding to last time, when he was saying, yeah, if you are near the well is interfering with the surrounding stresses. So maybe I should not use SH max, SH mean, NSV. Maybe I need to use other stresses, which is 100% right. He knew what he was talking about. It's just we don't know them yet in this class. That's what this last bullet point is trying to say. Like you may be near a geologic discontinuity, so the in situ stresses may not be, the in situ stresses in that area may not be true for that location. So it's anyway. What about shear failure now? We are gonna talk about, okay, the shear strength of the rock. Similarly to, remember we said that tensile failure is like this, like I have it like this and I open it like this. Yeah, it breaks. It has to do with the way the particles are held together, right? In the rock, we have something similar for shear, which is the way the rock particles are held together in terms of sliding. We call that the cohesive strength. We use CO or SO. And then when they start sliding, if like a slide in terms of shear, we have friction to that. And the friction is the same friction factor that you use in physics or kinematics, quantum mechanics, same thing, like mu. Newtonian mechanics, I meant to say. Same thing, dimensionless, mu. Remember, I was against using mu for the Lames second parameter because I told you mu would appear once more in this class, and then it appears many times in the reservoir classes. And I wanted to use capital M for the Lames because I knew this is coming up, you know, and it's coming up pretty quickly. So I didn't want to confuse you guys. Last year, I made the mistake of using mu for Lames, and then I had to use this for mu for this. And oh my God, it was, I went back and changed it, and I apologize to the class. Anyway, the frictional strength depends on the applied friction force, Ft, and where the force needed to displace an object resting on a surface depends on the normal force N that prevents the fall from slipping. This sounds complicated, but it's exactly what you learn in physics, okay? In physics, you learn I have this object. This is the surface, the object. I'm applying force Ft, and I have a normal force Fn. That is basically the weight of the object. And basically, the force Ft to make it move is basically mu times Fn, right? I have to make it move against friction. I'm working against friction. And the weight of the material is anyway, it's the basically preventing it from moving. Now I have this piece of rock, and I have this sort of fold that is like a. I have a fold. I'm putting a fold there, as in the how do you call it? As in a line of weakness, a bedding of weakness at the point of where, at the angle at which it wants to fail. And there is a reason behind that. Because in the rocks, in the Earth's subsurface, we have what we call the critical faulting stress hypothesis. We have an infinite amount of faults at infinite orientations and stress at infinite levels. So we can make the assumption which says that if I'm trying to create a fracture in the rock there, and the best way to make a shear failure in that rock there is to have a fault oriented this way, stressed in this level, and probabilistically it exists. And Dr. Lunster, who gave us a speech 3 weeks ago or 2 weeks ago, actually he was a big proponent of this hypothesis. He was saying it's actually evidence that he has is that it's basically a very, very logical assumption. Actually, he used to work for Zobak, who's a professor. His advisor is Zobak, and the critical faulting stress hypothesis came from an older Zobak student, like starts with B. His name Bailey and Zobak, 1995, something like that. 85, 75, I don't remember. But yeah, this is basically the critical faulting stress hypothesis. We are going to come to it many times this semester. It's basically a probabilistic thing. So somehow, if I apply a rock, if I apply stress to this sample, whether I have confinement or not, I don't care right now necessarily. Oops, sorry. But if the best fault, the best position fault is something that looks like this, and 60 degrees, what we were saying last time, and stress at a certain level, critically stressed, probabilistically it will be there. Okay, so I have now my force. This is my sigma NN I mentioned earlier. It's basically the same as this. And now these two stresses combined, they give me this tau. Okay, combined, both of them. They give me this shear stress tau, which I'm showing it as shear, but it's basically the same as FT here. And I need to basically compare them. I will do this, compare them. Okay, and now I will erase this. You okay, Malek? You have a headache? Huh? Did you drink water? Yeah, maybe. Well, the weather is changing as well, so wouldn't be surprised. Okay, if tau exceeds, then I have failure, slippage. The fault moves. The fault moves. And I have basically shear slippage along the fault. You may have heard the phrase fault reactivation. You may have heard the phrase fault slippage. You may have heard the phrase earthquake. Same thing. Earthquake is if it's very big, you know. But yeah, shear failure. Now, how are we gonna calculate? We said that this is a, let me use a different color. We said that this is in pressure dimension.
Is bigger than the friction and the
Times the,
multiplied by the normal stress is gonna create failure.
yeah. But how do you calculate tau and how do you calculate normal stress is much more complicated than this equation.
So it can be applied for like real faults.
Yeah, we're gonna see that.
Can we calculate that?
Yeah.
From real faults?
Yeah. Yeah, somebody did a lot of those actually to get them new for the rocks, barely from USGS.
By blocks?
Yeah, big blocks. You need ladders to climb on it. Yeah, he didn't.
No, not like experimental, like in the real. For example,
Oh,
fault of San Andreas. That's
no. But he did blocks of rock for real big rocks, and he was stressing them a certain way, measuring the failure. This is known as the Moore-Coulomb failure criterion. It's the simplest.
yeah, more cool.
Yeah. Let me write it down, and we're gonna see it many times. Moore-Coulomb failure, or I would say shear failure. Yeah.
So basically, it's the tau.
Huh?
Basically, it's the tau in Moore circle.
Yeah, it's the tau. Yeah, Moore circle.
Yeah, because you have the perpendicular to the touch point.
But what do you have on the x of the Moore circle? On the x-axis?
Your stress.
What stress?
Shear stress.
Sigma d.
Sigma.
No, on the x. What do you have on the y is this.
Yeah, between tau and yes, exactly.
We're gonna see Moore circles soon. Not
Normal
crazily
stress.
soon.
Yeah, normal stress.
Yeah, here you go. This is what you learn in physics, and it's no different than what we are doing now. And here is what I drew earlier, basically. Similarly, uncemented sediments can resist shear stresses with the application of an effective confining compressive stress. Even unconsolidated rocks, you can put them in vessels where there is fluid around them and mimics the confinement from the subsurface. They can still exhibit COs under confining conditions. So yeah, the maximum shear stress tau in uncemented sands, where basically I'm assuming that the tau naught is 0, it's important for this equation to be valid, is proportional to the normal effective stress, and the faults, I use 1n for the normal, and the fault's internal friction coefficient, sigma mu, often expressed as an angle phi, such that mu equals tan phi. So it's going to become clearer later. And for stability, I need to have this.
Yes.
But if I don't have stability, I will have tau bigger and I have failure. Let me ask you something. What if it's a cemented sand? Yeah, how does that equation will change? If it's a cemented sand. No, you have tau naught. Where is the tau naught gonna be?
The tau naught.
Here. It's gonna be the y, like a sort of a.
The tau naught is 0, right?
Yeah, but I'm saying, what if you didn't? What if this was the case? If it was cemented and this was non-zero? There you go. So now, the shear stress has to do with the difference of it has to do with the difference between, the biggest difference between the confining stresses. You have the code there, and you have three stresses, right? Sigma 1, sigma 2, sigma 3. So the biggest tau would be the one between the two, the biggest difference between the stresses. So sigma 1 and sigma 3 will yield a bigger tau than sigma 2 and sigma 3, or sigma 1 and sigma 2. So the more Coulomb failure criterion has this simplification, idealization, or assumption that it doesn't care about sigma 2. It only cares about sigma 1 and sigma 3. And many people have conducted studies to see if sigma 2 has an impact. In that, my former applied drilling professor, he was saying that he has evidence, but he wouldn't tell us because it wasn't published, about that sigma 2 has an impact on the shear failure, bigger than what we thought it does. I mean, according to the more Coulomb failure criterion, it doesn't have an impact at all.
Because it's a 2D.
Yeah. It's a 2D criterion. But in real life, how good is it?
It impacts, yeah.
Yeah, it does. I don't know how, but it should be. I can't imagine it doesn't, but of course, this is an approximation. Sorry, a simplification. And now we are gonna see what we have talked about graphically in what Malek was mentioning earlier. And hopefully it's gonna make it easier for you guys to understand. Okay, simple equation. We don't have a y-intercept, an offset. So why don't we do this? What we did when we were young, some people used y equals mx plus c. Some people use y equals ax plus b.
AX plus B,
Yeah,
yes.
we use the same. So sigma n is basically x. Tau is y. C is 0. I don't care about C. Or ax plus b, same thing. Oh, it's gonna lead to basically a line, a straight line with the slope equals to mu. Okay, this mu, the Greek letter mu, would be m, the slope. Okay. The Morse circle represents all possible state of stresses depending on the plane at which you measure tau and sigma n, the normal stress, from all possible state of the stress that intersects the shear failure line, which I'm going to show you. This indicates the plane at which shear fracture will form. I think I left this empty. Yeah, for me to draw. I didn't put the. I didn't put the. I didn't put anything, so I have to draw it. Okay. So we said y equals mx plus c. Okay. This is x. This is y. So this is u. So let me plot it. Tau sigma n. How will the line look like?
Slope.
What will be the slope? Do you agree?
Why? What's why?
No?
Why?
Who said y?
You draw why?
No, I drew mu. It's m. Is this? This is not y.
Yes.
Who said it's y?
No, sorry.
Don't worry. Oh, this is tau. I made it look like I drew it sideways. Yeah, this is tau. Let's call it. I'll put it here. Tau. The tau. Okay. Straight line. Very, very simple. Now, I need to add my stresses, okay? And I only care about two stresses, okay? Sigma 1, the most compressive, and the least compressive. I don't really care about anything else, okay? And I drew a circle like this, okay? Let's just say sigma 2 is here. Then it's gonna be like this, and then like this, but doesn't matter. The biggest tau, I'm getting it from the biggest difference between the two stresses. That's why I only care about sigma 1 and sigma 3. It doesn't have an impact based on the workload failure criterion. That's why I don't care where sigma 2 is. It can be anywhere between sigma 1 and sigma 3. It won't yield a bigger tau. So the biggest tau I can ever get, tau max, okay. Now, my circle remains on the right side underneath the line. Okay? It doesn't cut the line. That means I do not have failure.
Yeah. You are doing the whole experiment.
Yeah, in this case, I'm good. I'm very okay. Because above the line, I have basically the shear failure envelope. Like if my circle cuts in the yellow region, I have failure. So what if my circle, my sigma 3,
Was this?
yeah, what if it was less? What if my sigma 3 was here? Oh my God, look at that. I have failure. I didn't draw it very well, but it certainly cuts through, right? I have failure. And what are the states, the angles at which I have failure? Is basically all this overlap, I have failure. I have failure. Okay. So if I come and I have the distance between sigma 1 and sigma 3, I will use turquoise, okay. Okay, I'm between the two. And I have a radius. Let me take from here to here. Okay. These angles to phi. Yeah, we use phi for that. Are the angles at which my core, any fault in the core oriented in those angles will have failure. So it can be this, can be this, can be this, it can be this. Depending on the angle, I get failure. 2 feet. Yeah. Double the angle. Yeah. But the orientation of the fraction is 1 feet.
Yeah.
How about the tangent, the cotangent of mu,
The cotangent of u.
which is a phi, right?
Yeah, we said that a few slides
So
before.
it's not the same angle?
No, it's the same angle, but 2 feet. The phi, you are talking about this?
Yes.
Yeah.
So what average of phi is gonna be turned into 2 phi? This is phi.
Huh?
This is phi.
No, it's 2 feet in the diagram. When you read it from the diagram,
It's 2 feet.
Okay.
you have to divide by half by
Not in the
2.
core.
Huh?
Not in the core.
Not in the core, not in the core. No. The core is 1 feet. Yeah. The core is basically, let me draw it. I don't know how can I get back to the, there you go. Okay. It's the phi is from the. It's not the deep. It's the how do you call it? The huh?
Between the fault and the horizontal.
Yeah. Is the deep? How do we call it in geology? It's the deep angle, right? Or it's like imagine the fault. I don't want to.
Okay.
This angle
Yeah, it's a deep angle.
is the deep angle, right?
Thinking, yeah.
Oh, sorry.
That's one is
Phi. Yeah, in Greek you can write phi either like this or like this. Same thing.
Oh, that's lowercase.
They are both lowercase and this is the uppercase. But yeah, I meant the same thing. I meant the same thing. Okay. So I can have failure from. Oh, that's the mistake I have. Why it doesn't make sense. Sorry. So it's from, yeah, let me make it clear. I apologize for that. So this is the first phi. Let's just call it 2 phi 1. No, sometimes they use beta for phi. Yeah. And this one is the 2 phi. 2 phi 2. So, okay, this is phi 1. Maybe this is phi 2, right? That causes the failure. It's anti-clockwise of the horizontal line. Because you know these two faults, anything between those two faults is gonna fail in shear. Every other in between of those two is in the pink region. And then
So when we do this, are we changing the line or the circle?
Stresses. When
Yeah,
the
but-
stresses change,
Yeah,
you
but are
have
you
the,
changing the line or the circle? Or the circle is constant and you are changing?
well, the circle has to do with the stresses. If you change either sigma 1 or sigma 3,
It means that your line is constant at this position.
yeah, the line is given by this equation. If the mu doesn't change, the line is constant. Now, I'm not entirely truthful because to have this, it means that I have to have this, it's a tau not equals 0. So it's an uncemented, like, it's like saying to you, I have, it's not an intact rock. It's like it has a lot of fractures in it. Sort of the critically stressed hypothesis is valid. This won't be true with the core. It will be true with real Earth material, like big sample from the Earth. But with a small core, I generally consider it intact. So when I go to the lab to test the core, I need to take into account tau naught. So subject to mu along local pre-existing faults. PEF is a very common acronym or acronym abbreviation. It's called acronym if it's making a different word on its own, but this is a very common pre-existing faults. Natural fractures, basically. The more Coulomb criterion for frictional failure is given by relating the shear stress tau with the normal stress sigma n in terms of the rock's cohesive strength, mu and tau naught. Okay, so now I have this tau naught to worry about. So what's gonna happen is I'm gonna have an intercept. I have an intercept. I'm no longer starting from 0. Okay.
this tau 0, yes, if it's not equal to 0.
So if I'm doing a core or a small sample, I can assume it's intact. Okay, I can hold it in my hand. Huh?
Segmented.
Yeah, symmetric. When we say intact, we mean basically tau not bigger than 0, but not equal to 0. So you will have a failure. Failure. Y-intercept to your Mohr circle. But we are also in rocks. We also have pore pressure. How does the pore pressure affects the circle?
It shifted to the left.
Yeah, it shifts it to the left, and it causes to be closer to the shear failure envelope, which remains above the line. So the theory is the same. I just have a y-intercept too. This is the envelope, the shear failure envelope. If my line cuts through the envelope and goes up, I have failure. This is a thesis from a lady who worked on induced seismicity, on something that we are going to talk about a little bit later. Valerie Gono, her co-advisor is was our department's chair, or her old co-advisor is our department's chair. She did work on the Fort Worth Basin of Texas. No, father-in-law. I was saying in the other class, in the drilling class, we are doing about rheological models. And I was telling them, like, we talk about power law, Newtonian fluids, become plastic. And I was saying, what would happen if you have a power law and the index N is equal to 1? And the answer becomes basically Newtonian fluid. And it was like, it's like that guy in the, what's the name of that show? I forgot now. Shark Tank. He said, they asked him, like, who is investing? How are you investing? And he said, my wife's father-in-law has a factory in Romania or something. And they were like, dude, your wife's father-in-law is your dad.
Just to make it bigger. You can believe him,
Anyway. Yeah, you cross that line, you have failure, okay? Sigma 1 and sigma 3 are basically the in situ stresses, and they control the size of the circle. That's the whole thing about the Mohr circle diagram. It's a very simple and useful diagram. And you know, pore pressure makes you go closer to shear failure. Okay, so I don't think I have enough time today to do the example. But yeah, for rocks, like a big Earth subsurface, I can assume tau naught to be 0. Okay, because of the critical faulting stress hypothesis that I mentioned earlier. It basically says if I have a big chunk of rock as big as this classroom, maybe bigger than this as well, probabilistically, if the best oriented fault is facing a certain way, is stressed in a certain way, and it's made of material that is in a certain properties, I believe probabilistically there will be. And this is what Lundstern was saying in his presentation, that it's a very, very accurate, very, very realistic hypothesis, the critical stress faulting hypothesis. The Barley is the guy I mentioned earlier that did blocks. He was working for USGS. He passed on in 2015, I think. And in 1978, he published a book or a paper. He did a lot of experiments on rocks, big blocks of rock that you needed ladder to climb on. And he said for the rocks, for the Earth, like real rocks, geologic rocks, mu is between 0.6 to 0.8, closer to 0.6 than 0.8. So he said, okay, if you assume 0.6, 0.6, it makes sense to be there. Yeah. And okay, do we have time? Are they waiting outside?
So nobody will do.
Because I wanted to make an example of problem they did on.
Okay, so the idea is, let's go back to the previous slide very quickly. You see the impact of pore pressure? It moves your circle to the left. It moves it closer to failure, right? So imagine, okay, I'm moving like this. Moves me closer to failure. Okay, imagine this problem very quickly, since you guys are smart and you know what you are doing. Imagine I have this rock formation, it's shale. Sorry, it's very low permeability. And I drill my well. And then I fracture it, George Mitchell style. I do it transverse fractures. I'm very good at my job, okay? I have this well, I fracture it, I start producing. I produce this much oil. Sorry, no. I produce this much oil. Oh yeah, you're right. I made a lot of mistakes earlier today like that. I produce some gas too. I don't care so much about that, but I produce a ton of water, a ton of salt water. Okay, I need to do something about it. I'm in Dallas. I like Dallas. All my exes live in Texas. I landed in Dallas in 2010. Anyway, but I went in. I'm in Dallas. I'm producing a lot of water with my oil. I sell the oil, right? I sell the gas. I made a lot of money, but I need to deal with the salt water. Nobody's thirsty in Dallas. Okay, so if I want to desalinate it, it won't make sense, right? So what I will do, just like a good oil and gas, like independent company, 10 people in my company, I know all of them. We sat down together and they said, hey, you know what? There is this formation underneath the Barnett. It's called the Ellenberger, and it's very, very porous, okay? It's extremely porous. It has good porosity, good permeability. It's a very nice sand. Why don't you make some cheap vertical wells that are gonna be used to inject this salt water down? Okay, we make this vertical well, drill it, it's not terrible, and then come and inject this salt water into this formation. Okay, and I do that, and I start injecting, and injection goes well, no problem. Injection goes well, I carry on, no problem. 10 years, 20 years, and my friends, I tell that to my other company friends, because we go out at the same places, and I tell them this is the problem that we had, this is how we solved it. We drilled into the Ellenberger and we started injecting like crazy. We have been doing that for 10 years. It's a cheap solution for my salt water. But then suddenly the earth starts shaking, and they started blaming the frac job. They say we have been fracking here, and now we have earthquakes, and we did not have earthquakes before. So it must be the frac job. The truth is,
We move the circle to the right.
to the left. Now we are injecting into the Ellenberger underneath. I increase the pore pressure, and then I find a fault there that is ideally oriented, and the pressure goes up, it exceeds the Moore Coulomb failure criterion, and I have failure. So what happens is that I have this Moore circle, and now I don't need to have an intercept because tau naught is equal to 0. The Moore circle sigma 1 and sigma 3 was like this at the old pore pressure. But then the pore pressure increased. So my Moore circle moved to the right. This is the new sigma 1 and this is the new sigma 3. So pore pressure increased, Moore circle moved to the right. And now I do have failure.
So can we know if that failure is shear or tensile?
It's shear 100%.
Now how can we know from only the diagram?
Because the Moore Coulomb is for shear failure. But you can use it for tensile failure too. But the Moore circle is for shear failure. Because remember what you have on the y-axis is the shear stress. For the tensile failure, we're not going to do it in this class, but you need to look at the negative side of the Moore Coulomb diagram. You need to look here for the tensile failure. But whatever we use Moore circle diagram is for shear failure because it's shear stress versus normal stress. Anyway, so we get in this the critical faulting stress hypothesis. It says that okay, tau naught is equal to 0. I inject, I raise my pore pressure in the Ellenberger. And then if I need a fault that is ideally oriented, my fluid will find a fault that is ideally oriented and critically stressed. And then true, I have small motion, but it piles up, and after magnitude 3, I start feeling it. And the Dallas people feel that they are trespassing, and actually rightfully, because if they start shaking your house, it's like trespassing. It's like they walk into your house, you know? Maybe they did some shaking, but I mean, it was a lot. And then Oklahoma, and then Canada, they have that in Canada. We don't have it in Williston as much.
Well,
Induced seismicity from saltwater disposal. But yeah, Dallas was the main big thing. Fort Worth Basin. It was the main big thing. No, it's where the Barnett was. Because the Barnett was the first one, the first shell to be exploited. And yeah, they started injecting long time ago. When I was in the, excuse me, when I was in the engineering, geoengineering sort of consortium, it was called the FRAC consortium, Fracture Research and Application Consortium. I was doing hydraulic fracturing, tensile fractures, but we had a lot of people who are doing shear failure, induced seismicity. Valerie Gono was one of them. Moser Babazadeh, who's with Conoco Phillips, is another one of them. Other people from geology I didn't know that were one of them. Were on the engineering side of things. They were very interested. The companies that were part of the consortium were very interested in induced seismicity.
Seismicity, what kind of data gonna give you?
Data.
The P wave?
The actual seismicity? Well, that means like you need to model how much it moves and how fast it will move. We are only doing that if it moves or not at this level.
Yeah.
Because we're analytical. I mean, if you want to do this stuff, you need to write a code to solve it numerically. The slippage.
Like the purpose of induced seismicity.
No, there's no purpose. Induced seismicity is like a bad thing. You want to prevent it. Huh?
It's a
Yeah,
consequence.
it's the
Yeah, yeah.
results after
Injection.
fracking.
No, the result from injecting of salt water down. They were, when they were accusing it of being it's not the fracture that causes that,
It's the shear failure, it's not tension.
it's the salt water disposal.
Oh, it's not fracking, it's
It's
causing,
injection.
No, because fracking produces the salt water,
okay,
and then you have to inject the salt water somewhere. It's
okay.
the injection of the salt water. It's not the fracking. You fracture an impermeable formation.
So you will increase the pore pressure and the sigma 3 gonna decrease and you will have fractures.
Sigma 1 will decrease too.
Yeah.
They think it's the same.
Yeah. But it's not the shale that gets the seismicity. It's
Yeah, they're
the,
conventional. They cannot inject with something.
yeah, you're not gonna be able to inject. This is the element.
Yeah, below the barnet.
Yeah. This is the barnet. So,
So the water that they were producing from the fracking, they were injecting it
Yeah,
downstream, like,
yeah. And I used to have a student that looked at the wellbore integrity of this, because there was a lot of studies that said that they said that we model seismicity there and seismicity there, and we don't get it. And we model there and we actually get it. There is a spatial temporal lack of correlation, space and time, spatial temporal. So some people are seeing wellbore integrity and they are saying, okay, you may have wellbore integrity failures that happen before you expect to get the seismicity. So you have other things taking up your energy instead of fault slippage. So that could be an issue. Yeah. We didn't go very far, but
so I thought
that
that
is,
they were doing like water flood with that water.
you
That's
can do water flood, but generally water flood is you produce something and you inject something to produce something, so the pressure doesn't go very high. It doesn't increase the pressure during water flooding.
Yeah, that's
You-
what they were doing.
But injecting salt water disposal to stay, you increase the pore pressure.
Yeah, because a lot of research have been done about water flood, oil recovery,
Yeah.
from secondary recovery from salt water, and
Yeah,
like not salt, like normal water.
but it's not a salt water disposal project. You can use salt
They were
water
using it from
for fracture, for water flooding. But they're producing oil from
Yeah.
a different well,
They
right?
produce at some point water, yeah.
So you are not really increasing the pore pressure.
No,
But these people were injecting salt water for 16 years plus.
just seal it, just.
Yeah,
inject
for
it.
nothing else. They were not producing anything, they were just injecting. The Valerie's model was for 16 years. So it was a lot of,
But 16 years, it's not like
yeah,
10 or 5 or something.
yeah, even more than 16 years. Anyway, let's go. And yeah, I will see you guys we'll carry on this conversation on Monday.
So basically they were pumping into a balloon.
Yeah, and then you start having failure.
That's why there is your student who was like working on closed system.
Yeah, it's a closed
They
system
build up
because the
and-
pressure goes up. Yeah, the pressure has to go up.
They should build up and
Yeah,
they
and then you
found-
have failure in the wellbore and other stuff. Yeah, that you can have. If you have failure in the wellbore, it's a bad thing. You may get leaks to the surface, etc., but it uses energy. So it's energy that could have gone to cause an earthquake that won't make an earthquake because it was used elsewhere. It's like stealing your energy.
So it's easy to break the wellbore than breaking.
It's easier to break the cement than
Yeah.
breaking the,
the rock inside.
yeah, maybe. Or it's whatever will happen first. Yeah. And with that, thank you very much. I will see you guys on Monday. Don't text and drive, don't drink and drive. I was saying that to the other class.